Good afternoon, everyone. My name is Dr. Philip Phillips, and I'm the Associate Dean of the University Honors College. I'm very pleased to welcome everyone here today. We have a special program, and I have to say that one of the benefits of being a dean, especially a dean of an honors college, is the ability to arrange a special lecture on a topic that we believe is beneficial to our honors community, and that's exactly what happened in this case. Dean Weil and I were talking one day about the recent discovery of gravitational waves or ripples in space-time that were predicted a century ago by Albert Einstein. And we tried to wrap our minds around this, and we thought, you know, this is such a significant scientific breakthrough and it's something of such importance to our world that it would be worthwhile for us to invite someone who could explain this to us, and someone who could do so in such a way that those of us who are products of a liberal education, those of us particularly from the humanities who might have difficulty with some of the concepts, could understand. So I am very pleased to introduce someone today who needs no introduction. In fact, he was one of our speakers earlier in the series. Today we welcome Dr. Eric Klumpe, who is Professor of Physics and Astronomy here at MTSU. He has been here since 1999. That was the same year that I started at MTSU. And Dr. Klumpe is one of our finest professors at this university, and someone many of you know, probably if you're Buchanan Fellows, you've taken his astronomy class. But those of you who haven't taken his class, you've at least heard one of his lectures earlier on. And you know just how smart he is and how he can explain very difficult things in such a way that the rest of us can understand. So I won't take up any more time introducing him, but please join me in welcoming Dr. Klumpe.
It's always exciting to speak to I guess a classroom with this caliber, you know, the Honors College and all that. Very excited you're a part of MTSU, and you're all very, very gifted and talented people. It's just fun to be here with you, and of course, I always freak out when one of those guys asks me to do anything. It's like, but I'm happy to do it, happy to help out. It kind of bothers me just a little bit that we were hired on the same day, because I'm looking at what, or on the same year, because I'm looking at how much you've accomplished. You're like a dean kind of a guy, and I'm just a regular guy. So, but I'll try to get my act together. I got all summer to catch up, so I'll do that. I'll work on it. We actually touched on this subject just a wee bit last time I was here, because my intent of the last presentation I gave you is that any field of study in some way can branch into other fields of study. Maybe not all of them, but they're always conversation starters. There's always a way to connect good ideas with other good ideas. And astronomy is one of those areas. Astronomy has a huge impact on your life, whether you have noticed that or not. For example, current events. This is a significant discovery announced in February. And we're all going like, whoa, it sounds important because it's getting so much play, but I'm not really sure what it is. I think the last time I was with you, we made a connection between that and other ultimate questions of life that cosmology has a tendency to raise. Today we're going to do something different. We're just going to talk about the history that led to the point where Einstein was able to make the prediction, and then to go from there and see how that prediction was validated through an experiment. I have to have Volkswagen buses in almost everything I do. And the gravitational wave thing, I'm from Southern California. I surfed when I was young. Now that I'm old, I just look at pictures of surfing, especially since we're landlocked here in Tennessee. But that was my life. My bus was a very similar color. And my longboard, I still have it. When I was first married, it was our dining room table because we couldn't afford furniture. So we had, but the nice thing was when guests would put their feet on it, and then they said, whoa, I'm sorry. I go, no, that's what it's made for. And then they put their drinks on it, and they're worried there's no coaster. So no, they're designed to get wet. So it was a good thing, and boogie boards were my end tables. There you go. I know. True story, actually. I know it sounds odd. Oh, and the middle seat of my Volkswagen was our sofa. We lived in anyway, you don't want to hear about that. But, and here we go. Perceptions of space and time. This is where we need to start. All the way up to the 1800s, perceptions of how space and time operated were, I guess people thought they understood it. It was Einstein's, people say his brilliance. I have a tendency to describe him as being audacious. He's just willing to think differently enough to come up with an idea that just changes how we think about things. Einstein developed a theory about space, and it was about time, too. No, there's the connection. That's actually a very popular t-shirt, but I couldn't resist. What are known as Galilean transformations. I have a couple of pictures here, and this is common sense. And that's one of the things you learn about relativity. It challenges common sense. Because for you and me, our common sense is rooted in the fact that we don't move very quickly. When Einstein was developing this theory, humans had traveled at the blazing speed of a steam locomotive. That's how fast people went. Now we have, of course, air travel, space travel, but that's what they had. And so it was really amazing that he could say such things about what happens when velocities of particles or people get very large. All this picture is meant to illustrate is if the batter hits a baseball that travels at 30 meters per second to the right, the fielder is traveling 10 meters per second to the left, we can begin to talk about what's the relative speed of approach of the ball to the player in the red uniform. And you would all say 40 meters per second, and you would all be correct. Another example. Here's a guy in a pickup truck, and he's throwing the ball at 8 meters per second. Okay? The truck is traveling at 15 meters per second. This gentleman is standing stationary, which is 0. But you asked, how fast does the ball approach this gentleman? And you'd say, well, it's 8 plus 15, 23. And you'd be correct. These are called Galilean transformations. Okay? You're dealing with one perspective and connecting it with another perspective. You're dealing with one perspective and connecting with another perspective. But the implicit assumption here is that space and time are absolutes. Space and time are absolutes. Space being the distance between the two observers, and time being the duration a particle can travel between them. We'd say space and time are absolute. What changes, or what's relative between these two observers, is how fast things are moving. Okay? Relative to him, it's 30. Relative to that person, it's 40, and so forth. All right, now we're getting into what's known as relativistic transformations. Here we have a stationary person not throwing a baseball, but shining a flashlight. And the baseball in this case would be a particle of light, and it's traveling at 3 times 10 to the 8 meters per second. Compared to the baseball, that's extremely fast. Einstein was predicting at high speeds things behave just a little more differently. Over here, we have somebody in a spaceship traveling to the left at a very high speed. If the Galilean transformations are accurate, you would conclude that this person sees light traveling into her eye at 4 times 10 to the 8th meters per second, because Galilean transformations say you add, and that's the answer. So now you have an example of where somebody is observing light traveling faster than the speed of light. And according to Einstein's theory, that could never happen. An experiment was done before Einstein. It's called the Michelson and Morley experiment. People were concerned because I thought empty space was filled with some sort of a fluid, a medium, if you will. And that medium is called ether, the luminiferous ether, because experiments had been done that demonstrated that light behaved like a wave, just like ocean waves or sound waves. And one of the things we know about waves propagate through media. Sound waves propagate through air. Water waves propagate through water. Since we're observing starlight from objects that are extremely far away, and since light behaves like a wave, then there must be a medium between me and those galaxies. It's called the luminiferous ether. And then the thought came up that the absolute reference frame of the universe must be the one that is stationary relative to that ether. It's a little bit like swimming in a river that's moving. the absolute reference frame is the one where you're stationary relative to the river. And so what they did was, assuming that the Earth is moving relative to that ether, for 6 months of the year we're moving in one direction, for 6 months of the year we're moving in another direction because we go in a circular orbit, they would argue that the relative distance, the relative speeds you would measure of how light traveled on the two sides of the sun in our orbit would tell us how fast the Earth is moving relative to the absolute reference frame of the universe. What they came up with was the speed of light is constant for all observers all the time. And that's what inspired the theory of relativity. The fixed, the absolute, is the speed of light. What's flexible are space and time. Those things are what's flexible. Okay, for Galilean, space and time are absolute, velocities are relative. In the case of the Einsteinian approach, the velocity of light is absolute, hence space and time are relative. The TARDIS, time and relative dimensions in space. You know, we got this idea that even in pop culture, space and time have kind of a relative aspect to them, and the theory of relativity comes from this use of that word. Down here we go. Here's a TARDIS. There's a TARDIS in your office, and he goes, yeah, you bought a life-size TARDIS with our money? I did. Oh, Brent, this is just freaking awesome. Okay, and see, we can all connect with that. You know, why worry about the mortgage payment when you can have a TARDIS like this? Yeah, I totally get it. I mean, I'm with you guys on this one. Okay, but length contraction, this idea now that space and time, particularly when high speeds are involved, become flexible. Let me illustrate. This is a classic demonstration. It's kind of a thought experiment because trains don't really travel this quickly. But imagine a train, in this case it's 1,000 feet long, but you have a tunnel that's only 800 feet long. The train is larger than the tunnel. And the way this tunnel works is it has two red doors. At a particular instant, both doors, they're open virtually all the time. They're always open, so you can actually see through the tunnel. But at a particular moment, the doors slam shut and then pop open again, like the shutter on a camera. Okay? Chuk chuk, like that. And they do it together. All right? The first idea that we want to do is those two bars represent the length of the tunnel. Einstein argued that because space and time are flexible and because light is a constant, he argued that moving objects will always appear shorter, okay? When objects will appear shorter, or in the dimension that you're traveling, they'll appear shorter than if they were stationary. So the implication is that a train that's traveling from left to right, if it goes quickly enough, now this drawing of the tunnel, because the tunnel is its correct size, what's implicit in this drawing here is that the observer who's witnessing this is stationary relative to the tunnel because the tunnel still has its original size, its fixed size. But you see a smaller train. And when the train gets into the middle at some point, the two doors go chunk, chunk, and the train passes through without colliding with either door. Okay? And this is the idea that space is relative. But now we see another factor that comes to play. What if we put the observer on the train? Now it looks as though the tunnel is coming towards us at very high speed because if the train is moving on a level track at a constant speed, we can't sense that you're the one who's moving. So in this case, the train is still its original size, but the tunnel seems short. And what you're going to find out is if the speed of light is fixed and the speed of light is constant, what happens to this concept of simultaneity? Do both doors literally close and open instantaneously? If that were the case, in this particular frame of reference, the train's getting cut in half, right? But the way it works out, when you actually work through the equations as Einstein provided them for us, when the train gets this far from this reference frame, which is the reference frame that's moving with the train, you see this door close and open, and this one doesn't even move. And then just as the tail end of the train sneaks in, then this one closes. This concept of simultaneity, because time is now flexible, they don't close at the same time. The time at which it initiates the closing is flexible in such a way that the speed of light is constant for both observers. It sounds rather abstract, but you can think of this as like a length contraction paradox. It defies common sense because of the way we think about simultaneity and time. But when you study relativity, it's a trivial solution. okay? That doesn't mean it's trivial the first time you hear it, okay? But that's what's going on. But this is one of the things that Einstein was proposing. That's audacious, in my opinion. And that's why it was probably to our advantage that he was not in the tenure system yet. He was working in a Swiss patent office. So he could say things like this and publish. I'm not sure that would have played well. Another example, this is another common, when you're taking relativity for the first time, these are the sorts of problems that you work on as you're training your mind to think Einsteinian as opposed to Galilean. This spaceship is traveling at very high speed, but for the moment, we're taking the perception or the perspective of this particular gentleman who's in the spaceship. So from his perspective, the spaceship is stationary. It's moving at a constant speed. He has a timer, and the timer is a laser beam that goes up, reflects, comes down, it goes up and down over and over again. So like tick, 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 like a metronome. Tick, 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 tick. The time between ticks, let's say for him, represents 1 second. Okay? D1 in this case is the distance the laser beam has to travel, which is this distance. T1 is the time it takes to go from here to here. The ratio of those two numbers is the speed of light, which, according to Einstein, is always going to be fixed. Always the same ratio, regardless of what the observer is doing. Now we have an observer on the Earth watching the spaceship go over. Because the spaceship is traveling at a significant fraction of the speed of light, even though for him it's going up and down, for this person, the beam follows this path, reflects, and then comes down. Because while it's going up and down, it's going left to right. When you combine those two motions together, you get kind of a hypotenuse, where this is one leg of a right triangle, and that's one leg. See, kind of a hypotenuse. The first thing you notice is from her perspective, the distance the light beam travels isn't that much, it's that much. But if it took the same amount of time from her frame of reference as it did for this one, it travels a longer distance in the same amount of time, she would perceive that the speed of light is actually faster than c. But Einstein says that's not going to happen. That's not the way the universe works. Her ratio has to be the same, which means if this were, like, say, a factor of 10 larger, then this must be a factor of 10 larger. So she would see tick, tick, tick. So from her perspective, his clock is running slowly. Okay? You see how that just messes with common sense? The universe can't be that way because it doesn't make sense to us. But we, like you, like I, we were raised in an environment where things travel slowly and the Galilean transformations work perfectly. All the missions that I've ever worked on, Sun spacecraft, one of the spacecraft I worked on has left the solar system. One of the spacecraft I've worked on it's now dead on the surface of Mars. Another one is now dead in orbit. That tells you that I'm almost dead. And the way my knees are feeling, I think it's closer than I thought. But anyway, but we've never had to use the Einsteinian transformations to get there. And we always get the spacecraft to the planet exactly when we need it to get safely placed into orbit. So we learn if the distance is greater in this particular perspective, then time itself must travel at a more slower pace. So for her, this seems normal, but when she looks at what's going on here, when they compare notes, his clock is running slower because of her perspective. So moving clocks, the general rule is if you see a clock moving, it's probably, if it's going, well, it's always going slower, but how dramatic the slowness is related to how fast the clock is moving. Blasted Einstein, why can't you ever fill your time card out correctly? You know, I mean, you kind of get that, right? You see, can't figure it out. And eek, the test is over in 10 minutes, 5 minutes, 2 minutes. And he starts shaking his wristwatch as fast as he can. Moving clocks run slower, right? There's one in every class, yeah. Okay, now we're generalizing relativity. That's the next thing we do, because everything I've just described was referred to as the special theory of relativity, published 1905, 1906, somewhere around there. I think it was 1905. Generalizing it means now we're going to take into account that things don't necessarily move in straight lines at constant speeds, which is the situation we just described, but maybe we can talk about how things change in the presence of very intense gravity, like say black holes, or if things are accelerating at very high rates. There's something known as the equivalence principle. A lot of us don't use this term in this context unless you're a physics person, and there's a few of us in this room. But there's two experiments. Einstein, for him, this is a thought experiment. He imagines, in this case it looks like Isaac Newton because the apple is falling solely due to the attraction of gravity. Gravity is pulling on the apple, it falls at a particular rate as it tries to, there's a force pulling it towards the center of the earth. But he's in a box with no windows. All right? And then over here, we have a box with no windows and an apple, and it's accelerating through space like a rocket ship might do. Because the apple, in free space where there's no gravity, it would just float there. If this box weren't moving, it would just sit there. We've seen astronauts do that all the time. They'll place something there and it stays there. Those videos of astronauts in the shuttle. So what happens here, the apple is stationary, but if you can get this compartment to accelerate upwardly at the same rate that gravity pulls things down on planet Earth, you would see this apple fall towards the base of this chamber in the exact same way as this one did. And he argued the equivalence principle would demand that in the absence of windows, the observer has no way of knowing if the box is accelerating or if you're sitting on the surface of the Earth. So the physics the physics that explains one has to explain the other. It's not like, well, when you solve a problem, is it in a gravitational field? If that's true, use these equations. Is it accelerating through free space? If that's true, use these equations. The equivalence principle says they both should be treated the same. So there's no experiment that you can conduct to discern if the apple is falling because of gravity or because the room is accelerating, and that permitted him to model gravity from the perspective of motion through curved space as opposed to a force. This is where the idea that space is curved due to the presence of matter, like large galaxies and black holes, this is where that was born. Okay? Now we have to, again, that's very abstract thinking for us because we've opened the door to the fact that space is actually four-dimensional and not three-dimensional. And none of us in this room thinks in four dimensions. So it's very hard. The way astronomers and physicists and others try to explain it to us is they say, well, okay, since we can't think in four dimensions, let's reduce the problem to three dimensions, which means what I have to do is everybody in this room, I'd have to convert you into a paper doll, somebody that has height and width but no thickness. It's like I took a cookie cutter into some rolled out cookie dough and made a bunch of cookie people. See, we'd be two-dimensional. We would have width and height but no thickness. Okay? And we would live on flatland, which is the surface. Okay? Now, in the absence of any large gravitating masses, this surface would be flat, just like we are. And that would describe our universe. Okay? Planets would not appear as spheres because what we've done is we've dumbed it down to two dimensions spatially. So the third dimension can operate as the dimension of curvature, which is the curvature that Einstein was referring to. So we've got this curvature. Planets would be disks like coins. They'd be circular, but they would have no thickness. Okay? This dimension cannot be perceived by a flatlander who is in the surface. You can only encounter it by moving through it, but you couldn't see it. Okay? And so you have to do experiments to detect that curvature is there. Because we've removed ourselves, we actually have higher dimensional capability as people in the audience for three dimensions than the person who would be occupying that space. They have two-dimensional brains, two-dimensional thinking, two-dimensional experiences. But this allows us to see what would happen. But if we were two-dimensional like those beings, we would know more than we do right now, learning about the subject for the first time. But this is, as you can see, this is called an embedding diagram. And he's arguing that we can treat gravity not as a force, but as movement through a curved space-time manifold. The presence of mass causes space to curve. And the depth of that well tells you how massive the mass is. If this were a black hole, this thing would come down and it would not have an apex like that or a vertex. It would just be like a funnel. Curved space tells objects how to move. This was what he was suggesting. The presence of mass causes space to curve, and curved space tells objects how to move. The presence of mass causes time, which is actually time times c, to couple time with space. He had to multiply time times the speed of light, which gratefully is a universal constant, if Einstein's correct. The product of time times speed of light is also a distance, so now we live in four-dimensional space-time. Length, width, height, and c times time. It's our 4 dimensions, and which again is very difficult to perceive. And he discovered, just like the way clocks run slowly when they're moving close to to the speed of light, when we observe them as stationary observers, he also argued that clocks run slowly in curved time, which means if you're standing here, any clock around you runs normally, but the ones that are over here where the curvature is starting to manifest itself, over here you'd say, whoa, those clocks seem to be running slowly. You could even conceive of curvature so significant that time stops. And that's on the fringe of the event horizon around a black hole. Okay? And these are the sort of ideas that are now, people are building on a lot of the things, the foundation that Einstein had established for us. Special relativity applies out here. General relativity is required for the center. But actually, general relativity applies everywhere. When you simplify the equations to take into account that there's no large masses nearby, the equations of special relativity fall out of the bottom. They just fall out. So it's, look at that. Is that a crack in Einstein's theory of relativity? Nothing's perfect. And this one, I'm not sure what to do with this, but it looks like cats really wreak havoc on the universe. I mean, you see that embedding diagram? It's probably a bedspread, but it kind of looks like an embedding diagram, doesn't it? Yeah, I don't get it. I don't even know why that's there. All right, let's get rid of it. Okay, testing relativity. Okay, well, the conspiracy theory of relativity says, well, E equals mc squared, but of course he's saying that's just what they want you to think. That's the conspiracy theory of relativity. Yeah, you probably haven't encountered that. I can tell you guys aren't really responding to this one appropriately. Okay, the bending of starlight. This was in 1919. General relativity, around 1915, 1916. But Arthur Eddington, a British astronomer, was suggesting, well, if Einstein's correct, okay, remember, the Earth moves around the sun like this. The sun, because it's massive, it's the most massive thing in our solar system, should create the most dramatic curvature in space in our vicinity than anything else we have access to. The problem is when you try to look at how that curvature of space could affect what's behind it, you go blind. Your mom told you not to look at the sun, right? So don't do it. Do what your mom says, all right? But during a solar eclipse, the moon orbits the Earth. There's twice a year. The moon blocks out the sun exactly. And he was arguing, why don't we, because we know the shape of constellations because we've observed those constellations and photographed them when the Earth was on that side, let's compare those maps with what you would see on this side with the moon blocking out the sun. Of course, you have to have the capacity to measure angles that are very tiny. An arc minute is 1/60th of a degree. The full moon is a half a degree. An arc second is 1/60th of an arc minute. So the technology to measure these kind of angles haven't been around for long, but they confirmed that the shift in the star patterns matched exactly with what general relativity predicted. They actually observed in 1919, space is curved. The shape of the stars in the background. Some of us would call that gravitational lensing. Okay? Glasses change how things look. You see how I'm good looking and not so good looking? You see how that changes how things look? Yeah. Yeah. All right. This would be, if I go back one slide, I'm sorry about that. This is what if you think about it, there's an embedding diagram here. But the problem is, we, as occupants of that world, we don't get perspective. We get the top view. But as superior beings, temporarily, as three-dimensional beings looking down on a two-dimensional universe, that does allow us perspective. And we can see what's causing the lensing effect. Because light, like a coin, at those little funnels that you see in the mall, when you roll them in, they kind of go around in circles like this. Light coming towards us from this star would take this turn the way a car does on a racetrack with banked turns. So it kind of hugs the turn, follows a curved path, then comes towards our eyes. But because our eyes assume that all light sources the light comes from a straight line distance away from us, like this laser, we perceive the star to be there, when in fact it's over there. So we see the presence of this black hole, or this gravitating object, as causing the star field to kind of spread out, like this. And this angle was actually measured, okay? This is an experiment I actually got a chance to be a part of. Let me find, there we go. There's no sound. This is the Shapiro time delay. I was working, now you have to understand, when I was working here, I think my official title was the chief assistant to the guy who sharpened the pencils. Didn't fit on a business card. Now, I was 19, I was just hired, I threw my application in, and I thought I would love to get a job at the Jet Propulsion Laboratory. People said, don't even bother. Well, for some reason, 2 groups picked up my app, both of them wanted me, so they had a bidding war. So then I kind of got a salary increase without actually doing any work. But I got to be a part of and Shapiro at the time, he was a professor at MIT. But it was the Viking experiment. This is Mars. We had a spacecraft on Mars sending a radio signal to Earth. This is called conjunction, when Mars was opposite the sun. I'll run it one more time so we can see what's going on. But just to kind of tell you, we have a planet over here with a radio signal beaming off of it because we have spacecraft on the surface of Mars. This is the 1970s. I know did dinosaurs rule the world? I think they did. Okay, but what we noticed was you time how long it takes the signal to reach Earth. You timed it. And we could do that because we put a pulse on the signal as it goes out, and we look for that pulse when it returns. And we can measure how long it takes. Light from here to here takes about 8 minutes. From here to here is 8 minutes. And from here to here is about 4 minutes. I can time things on that duration quite accurately, and we did. And so what happens is you'll notice that it took the signal longer to get to us than can be explained by the straight line as the space crow flies distance. Okay, it took longer. And they go, that must mean space is so curved that there's no straight line path. It had to do take this little drop to get to us. Okay, I can show it to you again. Now that we understand it better, maybe we can watch it again and trying to get there it goes. But they're showing those little pulses kind of bunching up. They're bunching up from your perspective. But if this were an embedding diagram where we're looking from the side, you would see they're just going down in the divot and popping out the other side. That's all they were doing. They just look shorter because they're moving away from us, they're moving towards us like that. Okay? Okay, embedding diagram. This is what I was saying about a black hole. Notice we can't draw a bottom to that. And it gets so steep, even if the speed that light travels, there's no trajectory that takes you in and then back out again, the way like a car diving into a bank turn can come out. It's possible you hit at a speed that when you're inside, you can't come out. And that ring where that occurs is called the event horizon. And of course, we would argue the black hole would be at the base. It's the ultimate example of compressed matter. We can't think of anything. That doesn't mean it doesn't exist. But we can't think of anything that could be more compressed in terms of matter than a black hole. So you would argue that the effects of the gravity of a black hole on space-time are the most dramatic of anything we could imagine. And so these types of things occur. This is the most extreme example of space-time curvature. Space is so curved that light can't escape. Okay, so it looks like you've punched a hole in space-time. And if you could drop a clock down into a black hole, you would notice that it would eventually stop. Time itself would stop. Not because the clock was broken, but because that dimension that we call time, that process through which cause and effect phenomena occur, actually comes to a halt. And cause and effect actually cease to have any kind of relationship there. Some would argue mathematically that causation flips. Now you've got effects preceding causes. But I don't want to get into a discussion about that right now. But basically, a hole has been punched into space-time. So this is everything. It's a byproduct of what Einstein was suggesting. That's relatively small, relatively large, okay? And the infinite burger, so big it bends space. Now, don't ask. I have no idea what's going to do to your stomach. I do know it might add some curvature to your waistline. Been there, done that, got the t-shirt. I'm all about it. Okay. Anyway, detecting gravitational waves. Now, we are hopefully at a place where we can now begin to appreciate why he made the prediction, and then, of course, how that prediction was validated through an observation. LIGO, gravitational waves. Okay, Albert Einstein predicted their existence in 1916. Okay, right after the general theory of relativity. There's an experiment we call it LIGO. It's the Laser Interferometer Gravitational Wave Observatory. Okay, LIGO, and it was detected February 11th, 2016. Okay. There are two locations where these detectors occur, or they've been built. Hanford, Washington, Washington State, and then, of course, Livingston, Louisiana. Right? That's where they're built. The validation of the century-old prediction firmly establishes the role of general relativity as a physical law. I was persuaded long before this occurred, personally, just from the other experiments that have been done. There's been quite a few, so I was persuaded. So when I got this, I said, okay, well, I'm good with that. It doesn't really change my opinion, but we're in a place, we don't have to really talk about the theory of relativity anymore. It's more of a physical law, okay? Or you can say the principle of relativity, and that'd actually be more appropriate than saying the law of the theory of relativity. Say the principle of relativity, be more appropriate. They're located about this far apart, and there's a reason for that. And that's because this is the most sensitive motion detecting devices ever made. They're so sensitive that they can actually detect water waves striking the beach over here. They can detect those water waves. And over here, when they're that sensitive, you need to separate two of them by a large distance so you can filter out anything that one detects that the other one does not detect. Because a gravitational wave coming from far away, they're both going to pick it up almost at the same time. So anything that they both detect at about the same time is going to be a space-based source. Anything where one is versus the other, if like it's an earthquake, sound waves travel at a finite speed, those things can be filtered out now. This is called differential sensing. When you have two of them, and you can compare. That allows you to filter out false detections. 3,000 kilometer baseline. More details. Here's a sort of a miniature map. What you have is a light source. There's a light source, it's just a single laser. Here at the intersection is a beam splitter. It's a mirror, it's basically half silvered, so that 50% of the light goes straight through, 50% of the light bounces off. It reaches the end and comes back, reaches the end and comes back. The dimensions on both these arms, if you will, is so precisely known that in the absence of any sort of vibrations, fluctuations, or distortions in either of these arms, they both return here exactly they're exactly out of phase, in all honesty, because the result is they cancel and no light exits this side of the device. No light, because they exactly cancel. Okay, but it's 4 kilometers long, about 40 city blocks. The LIGO laser beams can detect motion on the order of 1,000th of a proton diameter. Now, you guys may want to check me on this, but I think that's pretty tiny. What do you think? Is it small? Are we good? Okay, we're good. All right. I wouldn't know. I've never really looked at a proton either. So, but 1,000th of a proton. I can show you how to do that calculation, by the way. Anyway, sensitive enough to detect waves hitting nearby beaches. We got to get a beach theme into everything I do. There it is. Okay. And here's the setup again. Okay. Ideally, there's a light source over here, not illustrated. The detector's down here. The beams go all the way to the end, and they originally started in phase because they began from the same initial beam. But when nothing's going on, the A and the B are exactly out of phase. You see that? So when you add them, you get nothing. And so sometimes this is referred to as the dark port. When no light is coming out, that means nothing's happening. Nothing interesting is happening. But the minute something interesting happens, like let's say some guy drops his burrito on this arm, okay, boom, you get a detection, and you see the light coming through, all right? If you get something like this, two signals that are slightly out of phase, you can get a time-varying signal like that. That actually comes quite close to what black holes create, at least merging black holes. This is sort of another illustration. The dark port would be here, so you got the incident beam. This means nothing's happening, it's boring. But if you can compress this one, light comes out. If you compress this one, light comes out. And so you're hoping that something that has an influence on either one of those arms will be detectable, and you're hoping the influence is gravitational waves. Binary black holes, this is a video I found. Oh, great. Great. I just want that. You can see gravitational lensing in the background. I want you to notice, it's kind of difficult, but as the black holes get closer and closer together, they go fat, they speed up. And notice once they merge, the system becomes quiescent. Once they've merged, okay, it becomes stable. But when there's two of them, what happens is they're doing this. If I can make my own little movie here, this isn't quite as exciting, I know. But the two black holes are doing this, but as they fall in on each other, notice how they speed up, okay? And then as they merge, then it becomes one, stationary at the center of mass of the system. Okay, and nothing happens. All right? Well, imagine these two guys. Again, this is very surfing. My wife always freaks out when I'm out there. I see dorsals all the time. I don't know what it is. They don't even frighten me. Probably because I've never been bothered, but generally they're always porpoise. But you do have to worry about, in California, not as big a deal as Florida. Florida, there's particularly Cocoa, which is where I like to go. Sharks are quite common. But I've never been bothered, and I don't, for some reason it doesn't even bother me. I don't even think about it when I'm out there. But imagine these two things circling, okay? Because there's two of them moving about a fixed point, they create ripples in the water, and those ripples go outwardly. Okay, if you were smart, let's say you're like a shark expert. All of us are shark experts at least once a year, right? And when is that? Shark Week. Yeah, don't call me during Shark Week. I'm watching shark shows. Okay, but aren't they the same ones that they had like last? Yeah, but they never get boring. Okay, but you can see this, and so with the black holes, it's kind of analogous. See, if these masses curve space, and the masses are moving with each other, then these curves are being dragged in the same way the presence of a shark could generate like a bulge or a wave on the surface of water. These guys are creating disturbances in space-time that move outwardly in the same way, which means anything that's in its path is going to experience a stretching and a compressing of space as it passes over you, okay? But we need something that's hypersensitive to detect it. We're not saying that this just started occurring recently. This has always been going on. It's just that we don't have the technology to detect it, which is why it's very important to recognize that a lot of great discoveries are born out of the fact that technology is always improving. Our computers are faster, our telescopes are more sensitive. Now we have gravitational wave astronomy. It's a branch of astronomy that has now just been born. Here's sort of a picture. You've seen it before. The light source, the beam splitter, it goes this way and back, and the detector's over here. What you're hoping is these gravitational waves, as they move through, are going to create compressions, okay, stretching, making, in the most minute way, the length of this path just ever so different from this one, and the dark port lights up. Light comes out. And this is what was detected. This is the actual signal in Washington. This is the actual signal in Louisiana, at least the blue one is. The orange one is this one inverted, because they were showing that because they're not located on top of each other and because their arms are oriented differently, it actually came flipped. It detected the exact same signal flipped, which is kind of neat. You're thinking we designed it to do that, and that's what we're seeing. This is a mathematical model of what they thought merging black holes would look like. So you're comparing the model with what you actually observed. And that is way cool. Notice, what you've got here is, As they get close, as we move to the right, the black holes are getting closer and closer and speeding up. So as they get closer and closer, okay, we're seeing the energy increase. As they're speeding up, we're seeing the distance between successive peaks shortening. But once they merge, it becomes quiescent again. Just like you would think. I mean, you guys understand that, I think. I think you can picture that in your head, okay? The strain is a technical term that means the change in length divided by the original length. We're dealing with numbers on the order of 10 to the minus 21. We're seeing strain on the order of 1 times 10 to the minus 21 because each of the arms, 4 kilometers, that represents 4 times 10 to the minus 18 meters in terms of stretch. A proton is 1 times 10 to the 15. That's why they say it's 1/1000th of a proton, because it's the amount of motion was just 1/1000th or 1/10 of 1% of a proton diameter. But they picked it up and it fit what they expected. Now, what was observed? 2 colliding black holes merged to form a single black hole. Does anybody know how black holes can form in pairs? I thought when black holes formed, there was a supernova. Why wouldn't the other star have been obliterated? Well, we now know that maybe we're not thinking about that problem correctly, because we have evidence that black holes occur in pairs. That's cool. The event occurred 1.3 billion years ago because the waves, you can estimate by the dynamics of that system how massive the black holes must have been, okay? And you can estimate how much energy was released by the collision of those 2 black holes. And you take into account how far away it is, that explains the amplitudes that we see here on Earth. Or maybe the amplitudes we see on Earth tell us how far away it must be, and that's the way it was done. So it's 1.3 billion light years away, meaning this event occurred 1.3 billion years ago. No, I was not alive. I know, just in case you were thinking it. Dr. Val was. Yeah, well, all right. Way to go, bro. Okay. Can I have the number of your your doctor and stuff? I mean, it's like you're doing all right. Anyway, the energy from the merge was the equivalent to taking 3 of our suns and converting them into pure energy. Okay. One of the things we do, I teach an astrophysics course here. It's a 3,000 level course, and we actually do these calculations. We actually talk about, if the laws of thermodynamics are to be upheld in the presence of black holes, how much energy is emitted when 2 black holes come together, because all the conservation laws of thermodynamics must be sustained. And so it's kind of a fun calculation, but I get that. You can anticipate how much energy must be emitted. The energy hitting LIGO was greatly reduced because the light, you ever notice when a car is like a mile down the road, the headlights don't hurt your eyes, but as it gets closer it does? That's because the energy from that light is spreading out over a very large distance as it travels towards your eyes. So by the time it got to us, even though this sounds like a massive explosion, a massive amount of energy being emitted, by the time it reached us, it wasn't very significant. And that's why we don't feel it on a daily basis. We learned that black holes exist in pairs, and gravity wave or gravitational wave astronomy has been born. A brand new frontier has just opened up. We can now build telescopes, if you will, telescopes to measure the Big Bang. Because wouldn't that produce gravitational waves? Yes. And that's kind of cool because observationally we're somewhat hindered. You can't look farther back in time using light than the actual period when the what's called the primordial fireball became transparent, when the background radiation associated with the bang itself, the so-called smoking gun, became transparent. And that's not quite as far back in time as something like this would permit you to look. This is very, very exciting. Yeah, I just said that. Now, what did not happen? I have no idea what you think, but I try to anticipate. This is a story that I don't think happened, but let me see if you think that's what you think happened. LIGO was completed. Yay! Okay, who gets to cut the ribbon? I don't know, but somebody does. It was turned on. Click. I don't know about you, but I always hit the red button. Whenever I'm in a room for the first time, I always look for the red button. Because when you hit the red button, something interesting always happens. In this case, I suspect LIGO was turned on. Scientists saw nothing for days. They go, I wonder if we did this right. Doggone it. I'm taking lunch. Suddenly, out of nowhere, a signal was detected. You're kidding me. No, I'm not. lo and behold, it just happened to be the signature of two merging black holes. Because when I listen to people, when I overhear what people are saying, it's like, why is it that we just detected it? We just finished the thing a few months prior. Why did it suddenly appear? Well, maybe the right answer is because it's happening all the time. And maybe actually identifying an event that creates gravitational waves is not as easy as we think. Because what you have to eliminate are the ocean waves, that mosquito that burped 100 miles away. We've got to get rid of that. You know, you got to eliminate these sort of sources. What's more likely that happened was LIGO was completed. Yay! The yay is for both. We can yay both of those, okay? It was turned on. Yay! And we know which button it was. The red one. Okay? It immediately started to yield detections. They probably had to do some calibrations. They're going like, whoa, look at this. I wonder what that is. Non-gravitational wave detections had to be identified and eliminated. So you begin the process of eliminating false detections. Of the potential gravitational wave detections, the simplest one to recognize is the one that all of us now understand. Two black holes going faster and faster and faster, producing an increase in energy, shortening of periods between, and then merging to become to a quiescent flat line afterwards. We all know that. They knew that. Once they saw that, they said, that's it. There are other things in the data that are being produced by, you know, extraterrestrial sources. I probably shouldn't use that word. I'm so sorry. Okay, the aliens, whatever. Anyway, but there's other signatures we need to understand, and those signatures are also present. The signature of two merging black holes is easy. That's why it was found first. There's other things out there. The signature was identified within all the available data and reported as a detection. The end.